Okay, so to continue where we left off, remember we started off by talking about electrophilic addition. Then we talked about a few different reactions, H2SO4, talk about the first two reactions on the reaction sheet, HBr, and then adding HBr, what happens when we react it with peroxide. And so far we haven't talked about reactions that are stereospecific, meaning the product will have a certain stereochemistry. The closest thing we got was the last reaction we did, which was uh, the last reaction on the first page, H3O plus. And that reaction involves adding OH to the more substituted side. So it's Mark addition with OH. However, that one can't control stereochem. So now we're going to get to the first reaction we're going to be dealing with, that now stereochemistry does play a role. And this is the first reaction on page 4 of the notes, called oxymercuration/demercuration. So I'm not going to go over the mechanism for this one just because it's kind of weird, and I don't think you need to know it. It's a complex mechanism. That's what it says on the reaction sheet as well. Let me get a better pen, thicker pen. That's better. Okay, yeah, so oxymercuration. Mercuration. So what this involves, you'll have, for example, an alkene still. We're still dealing with electrophilic. And you'll notice the reaction sheet likes using D a lot. D, again, just deuterium. Remember from last exam, just like a heavier hydrogen. Okay, so this reaction, so far, the ones we've been dealing with, they've just been like one step. Like the things you're adding just have happen together, like one step. Like H3O plus, HBr. This one, it's a two-step reaction. So I think you can get away without knowing the mechanism because it's complex. But what you do need to know is that you have to number this reaction. So step one is you have HG OAC. Remember, AC here is acetic acid. OAC is just an easier way to abbreviate it. Slash H2O. Step two, NaBH4. So it's like if you don't know what this stuff is right now, over time you'll just end up memorizing it. But now what's special about this reaction adds OH to the double bond. So it gets rid of the double bond to add an OH, and it's going to add it Mark. This is a Mark addition. And now the other thing you need to know is that it's anti-planar. If you remember anti from last exam, if you remember, E2 had to be anti-coplanar. So that meant the leaving group and the BR had to be opposite to each other. This one is the same. So you're adding OH and an H. And so the OH, like for example, if we have CH3, remember we had CH3 here on one side of the double bond. So that means OH has to be on a dash. And then here, if OH is on a dash, what does hydrogen have to be if it's anti? Yes, correct, wedge. Which means that deuterium is on a dash. Here, deuterium is to differentiate between hydrogen and deuterium. So you know what's coming on a H, what's coming on a wedge, what's coming on a dash. So the important thing to realize here is One, this reaction's mark, and it's anti-planar. So anti meaning you're going to add OH to the more substituted side because it's mark. And remember, because it's a double bond, you have to also add an H. So the OH and H are going to be anti to each other, meaning if one's on a dash, the other has to be on a wedge. This is if it's on a ring. If it was just regular, like a non-cyclic structure, you would just show one going up and the other going down, for example. So keep that in mind. Mark, anti-planar. Now, if you read the reaction sheet, there are certain reactions, like for example, the one HBr with peroxide, how it's the peroxide makes it non-mark. I specifically call it non-mark. The reaction sheet on the left, it'll say anti-mark. I prefer not to say that because you might mistake anti-mark with anti-planar. So I just avoid that altogether. If I'm saying anti, it's referring to anti-planar. If I want to specify what peroxide and HBr does, I'll say non-mark. So like they make mark the opposite of mark anti-mark. I disagree with that. I think it just makes things more confusing than it needs to be. So just get in the habit of saying mark or non-mark, and then anti and syn. Anti meaning their opposite, syn, same. So hopefully that's easy enough. Okay, now a couple other notes about this reaction. An easy kind of way to remember whether it's mark or not. Hg, if you remember, it's mercury. That's why it's called oxymercuration. So if you remember, mark. I don't know. That's like the way to help you always remember. Merc means it's going to be mark. So mark. Just keep repeating that; it'll eventually stick. And then here you notice this has /H2O. So let's say I drew this reaction like this. What's coming off? What do you think will come off on the dash here? You have any idea? Correct. OCH3, but yeah, I'm hoping that's what you meant. So if you can tell what the difference was, when this was /H2O, think of like how in SN1 you had an H2O in heat, but that would still result in OH being added. Because the complex mechanism part of it is that this H2O will attack and then it ends up getting deprotonated. So imagine the oxygen being added, but then it'll have 3 bonds. So to make it happy with 2 bonds, one of the hydrogens coming off of this oxygen will be deprotonated to give you OH. Same logic. Again, notice they're both protic, so they both have this H. The oxygen will attack, but then it'll have too many bonds, so this H will get deprotonated to give you OCH3. So this is, I believe, one of the few reactions, maybe the only, but one of the few reactions that will allow you to add OCH3 to a double bond. So far, we've already learned 2 reactions that will add OH to a double bond. So kind of try to, if you will, categorize the reactions so it'll make them easier. Like that way, if you need to know what reaction do I know that adds an OH, you can immediately off the bat remember this. I feel like sometimes when you categorize them, they help. Like for example, right now we're categorizing all the electrophilic addition reactions together, and then you can even sub-categorize them even more. So I don't know. That's how my mind works. It helps helps make it easier. But yeah, so understand mark, oxymercuration is mark addition with OH or with whatever is in this first step with the with this mercury acetic acid thing. But yeah, that's pretty much it. And then anti, remember it's anti-planar. So this OCH3 is anti with the H. This one's on a dash, this one's on a wedge. So they're going opposite. Yeah, that's pretty much it. This is our first reaction that we're learning that's stereospecific. All right, so continuing on, our next important reaction is hydroboration. So just like how we learned how we first learned how to add Br in the mark addition, meaning to the more substituted carbon. The reaction we learned after that was how to add Br to the non-mark position, meaning the less substituted position. So similarly, we learned two reactions that will add OH to the more substituted position, H3O plus, and this mercuric acid, acetic acid, H2O thing, oxymercuration. Now we're going to learn hydroboration, which involves adding OH to the non-mark position, the less substituted position. So let's go over this one. So let's say we have a double bond now that looks like this. If you add BH, again, this is a two-step one. Step one, BH3.THF. Step two, H2O2/OH minus. Now this is the key. H2O2 is hydrogen peroxide. Again, whether you see ROOR or H2O2, that should be a red flag alerting you that this is going to be non-mark. So that peroxide, whether it be hydrogen peroxide or some sort of CH3OOCH3, for example, ROOR, that's a red flag that this is non-mark. So this OH minus tells you it's going to be non-mark with the addition of OH. Now here, it didn't matter because both these sides are equally substituted. But what's also important about this reaction, remember above with this merc, it's mark addition and anti-planar. This one is going to be non-mark, and to confuse you even more, this one's going to be syn addition. So if it's syn, that means we're going to get something that looks like this. The H and OH will be on the same side. If it was anti, the H and OH would be on opposite sides. So it's syn. Same side. Okay, so now let's see this in action when we have something that's substituted. So again, go to the same example. BH3.THF H2O2/OH minus. So because it's syn, that means your H and OH will be on the same side. So for example, if I put CH3 there, and H here, then D is here, and then OH is here. So notice OH is added on the non-marked position, and its syn is coming off a dash just like the H. So again, keep that in mind. This is hydroboration. Notice how these two are stereospecific and how one is marked, the other is non-marked. All right, continuing on. Another electrophilic addition reaction is now the addition of XX. This isn't something adult rated XXX. This is just XX, right? XX meaning a halogen. So Br2, for example, Br, sometimes Cl, and sometimes I2, II. Okay, so this one, I think the mechanism is important, so I will go over it. And this is the third reaction on your reaction sheet. So this one, it is going to end up giving you something that's anti. So that's important. This reaction's anti. Okay, so what does this mean? So let's go over this mechanism. So you're going to have something that looks like this. Let's say you have a double bond here. Okay, so over the arrow, this reaction has Br2 and CCl4. CCl4 is the solvent, carbon tetrachloride. It doesn't really do anything in the reaction, but the reaction won't happen without it being in that solvent. So you have here CCl4, then you have Br bonded to Br. So what's going to happen is the double bond here. So let's see. Sorry about that. Okay. Okay, so what's happening in this reaction is going to be a little bit confusing, but bear with me. Remember, we're used to seeing something slightly negative attacking something slightly positive, or like a source of electrons, so like this double bond attacking something positive. So what's happening here, when you have Br bonded to Br, one has to be kind of slightly positive, the other has to be slightly positive, slightly negative. Even though technically they're the same, there's no difference in electronegativity. With this reaction, that's how it happens. So what's happening is that this double bond is going to attack the Br. And as this attacks the Br, this Br is going to attack this carbon. So as that happens, this has to give up its electron, because the Br is bonded to this, it's going to break up its bond with the other Br, and now you end up with Br minus. So now bear with me here. This is going to give you what's called a bromonium ion, which looks like this. Because Br now has two bonds, it only likes one, this has a plus. And now remember, we have Br minus now left over. So what's going to happen is this Br minus is going to attack from the back so that this Br can take its electrons back because it doesn't want to be bonded to this. So it's almost like an SN1 reaction where it attacks from the back and kicks off at the same time. So because of that, you end up with something that looks like this. Because this attacked from the back, it's like inversion. So it became on a dash instead of on a wedge. So anti-coplanar addition. So to make it easier on yourself, let me just do it. So if you need Br2 and either CCl4 or CH2Cl2. More commonly, you'll see CCl4. And then that gives you oh, sorry, there's no stereochemistry because of the double bond. Then it becomes stereochem. So notice all that happens here is that you add two BRs on the double bond on each side, one BR on each side of the double bond, and they're anti. In case that's why I think the mechanism with this really helps you to understand what's going on, kind of. It'll make more sense once she goes over it, but again, what's happening is you form this what's called bromonium ion, and then the BR from the other BR wants to attack, and that's how it ends up being anti. Yes, yeah. So as long as the two BRs are anti, it doesn't matter. That's what dictates the stereochemistry. Okay, so continuing forward, a similar reaction. This one is addition of XX. A similar reaction is called halohydrin formation. And halo meaning halogen, hydrin meaning OH. So this is X2/H2O, addition of XOH. So now, if you have let's say something that looks like this. And you have, let's say ClCl, H2O. How does this reaction happen? So let me show you. Similarly, you're going to have what we just saw. This Cl attacks the carbon, while this double bond attacks the Cl. Let me do this. It might be better to show like one of the lone pairs attacking. And then this gives up its electrons to the Cl. So now you end up with not that ugly of a hexagon. Now this ring again, you have that Cl ion. And now notice you have the difference between this one and the other one. Now you have this H2O. So if you have H2O, which side do you think it's going to attack? The first carbon, or this carbon? Because again, Cl has too many bonds. So something has to attack to let the Cl kind of break away and just be having one bond. So on the other side, attack from the back. Here, which side do you think is going to attack? Any ideas? Attack carbon 1 or carbon 2? What's the difference? Let me ask that. What's the difference between carbon 1 and carbon 2? What kind of carbon is carbon 1? Primary, secondary, or tertiary? Yes, tertiary. Carbon 2 is secondary. Notice carbon 1 is bonded to this carbon, and CH3. This one is bonded to just 2 carbons. So this one's tertiary, this one's secondary. So which do you think oxygen would rather attack? Think of like an SN1 reaction. Correct, carbon 1. This is going to attack this carbon. Because it attacks that carbon, forces this to go. It's still like a backsided attack. So, continuing forward, you now end up with the CH3 will now end up rotating to get on a wedge. And now you have O with 2 H's because we haven't done anything with that. And then we have that Cl is now here. So then we can either use the remaining Cl to deprotonate, or we have a lot of water. So either or we can use to deprotonate this to give us our final product, which looks like this. So this is a very similar mechanism to the one above. The difference now you add H2O to the mix. So this halohydrin formation, it is mark addition with OH. So OH is going to be added always to the more substituted side. And on top of that, it's anti-coplant. It's the Br and the OH are anti to each other, or like the halogen and the OH are anti. So notice OH got added to the marked position, the more substituted position, and the OH and Cl are anti to each other. So again, comparing to this one, the BRs are anti, but it doesn't matter which one's more substituted because you're adding the same thing. This one, the two things are still anti, but the difference now, it's marked with the OH because the OH is now going to attack in the most substituted position. Does that make sense? All right. The next reaction she has over here is addition of carbenes. Let me look at the reaction sheet. Hmm. This one's kind of all right. So this is on the third page of the reaction sheet. Again, like I said, this is not really that ordered, but because I want to kind of follow along with what she does in the notes, we'll go over it. So a carbene is, so it looks like this. So you start with your alkene, and now you treat it with something called diazomethane, which looks like this, CH2N2. Now if this reaction has heat with it, it's going to form something else like this. That's called a carbene. So in your reaction sheet, this is called carbene/carbenoid addition, formation of cyclopropane. So you're forming this thing as a cyclopropane. You're forming a cyclopropane on this what's it called? This cyclopentane, sorry. Or in this case, hydrid cyclohexane. So the carbene is what's formed in between. So let me show carbene. So carbene's like the thing that happens in the middle. But yeah, this reaction is more of just knowing what happens. Like here, the other way this can also happen is through this reagent called Simmons-Smith reagent. So another way for this to happen is you have CH2I2, and then this zinc Cu. So this is called the Simmons-Smith reagent. The mechanism for this one's also kind of complex. I would just memorize this. This one is syn. Like these are wedges. But yeah, called carbene formation. So this was when you have a cyclohexene. Let's see how this looks if we had just a regular double bond. You end up with this. So notice, what's it called? Stereochemistry is preserved. So what that means is H and CH3 going up, H, CH3 continue going up on a wedge. CH3 and D go down, CH3 and D go down on a dash. So this forms cyclopropane from a double bond. So if it's a ring, it'll be attached to the ring because the double bond doesn't just like separate. So this is carbene. It's called carbene addition. It forms a cyclopropane. But yeah, okay. So again, you're gonna realize a lot of these reactions you just kind of have to memorize, and I think this was one of them. But hopefully, with more practice, it'll make more sense. Okay, so continuing on with carbene, we now we have a dibromocarbene and dichlorocarbene. So this is on your reaction sheet. The second reaction on page 4. So this now looks like, let's say you have this double bond. So if you have CHCl3 or Br3, so the Cl could be replaced with Br, you'll form something that looks like what we have above. But now you have this dichloro or dibromocarbene. So again, the reason why she does these right after each other, because they're kind of like the same category. Give me 1 second while I charge my laptop. So this is called the formation of dichloro or dibromocarbene. So if you have CHCl3 with potassium hydroxide, this is how it forms. The mechanism for this one, does she show it? She does show it. Again, if I like the ones that I don't know the mechanism for, it's generally because you didn't need to know it. So it's up to y'all if you want me to go over the mechanism or spend more time trying to go over problems. But at this rate, I kind of want to use the reactions we've learned to start practicing. So I think we've gone over enough to where we can start practicing. So okay, so let me pull up Zaid Faraj worksheet. We're at chapter 8. Okay, so try this out. Oh my gosh. No, not that way. Okay. Here. There we go. All right. So you have 4 arrows here. So tell me, going up, going down, going right, going left, what do you get? I'll give you all a minute to try and implement what we've learned. Again, obviously try to do it without looking at your notes. All right, so I'll start with going right. So what does this reaction add? Huh? H3O plus, what does it add? Anyone? I mean, there aren't too many options. What do you see in H3O? Yeah, fall asleep on me, what's going on? So I'll answer for you. H3O plus adds an OH. Now the question is, where does that OH get added to? And the answer is, it gets added to the more substituted side, which is this carbon. Now, what's important about H3O plus is stereochemistry. Here, it's not stereo specific. You can't control stereochem. So as long as you show it being added to this first carbon, then you're good. So this carbon is going to have hydrogen, hydrogen, CH3, OH, CH3, CH3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Easy enough. All right. What about, let's go down. What does this reaction do? Y'all still here? Y'all can hear me, right? Okay, good. Adds Br. Where does it add the Br? First carbon or second carbon? First, yes. Because this one, we don't see peroxide, so that must mean it's mark. So it's going to add it to the more substituted position. This one, H2O plus, was also mark. So actually, this is wrong. CH3, so Br, CH3. Okay, so going up, what do you see? What is this? Peroxide, yes, ROOR. So that means, because this Br was marked, This makes this non-mark. Essentially just switch the Br and H. Yep. All right, so now Br2CCl4. Do y'all remember what that does? Yes, so it's anti, and you're going to add a Br to each side of the double bond, each carbon. So the way you can show this, show Br there, Br there. Then you have CH3, 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 H. Notice Br is going down, Br is going up. They're anti. So that's a good recap of the 4 reactions we've done. Let's continue. Let's say we wanted to see, oh no. Let's say I wanted to see, what if I said, what does HgOAc /CH3OH NaBH4. What is this reaction going to do? And the chrome is exactly. So it's going to add OCH3. It's anti to the H. What's on the second carbon? you correcting yourself, right? So the OCH3, remember this is oxymercuration. Mark. So the OH is going to be added to the more substituted carbon, which is the first carbon. So the hydrogen's on the second carbon, and they're anti to each other. So this one will kind of look like the BR1, where the OH and the where the BRs are anti. But now you're going to have OCH3 because we look at here, we have CH3OH, so that's what's going to be added. So then you're going to have, the H here is going to be anti to the OCH3. And the OCH3 is added mark. Just like that. OCH3 and the H are anti to each other. Man, what is going on? Okay, let's say we had the last reaction we learned, which was BH3.THF H2O2/OH minus. What will this look like? What's the first thing that should be a red flag in this reaction? peroxide, yep. Hydrogen peroxide. That should tell you automatically this is going to be non-mark. And what's special about this stereochemistry? Syn, correct. So we haven't seen one that's syn yet. So let me show you syn. So now the OH is going to be on the less substituted carbon. So this one. And it's going to be syn to the H. Notice the OH and the H on the same side, and the OH is on the less substituted carbon. So we just saw 6 reactions taking place. Let's see if you can do this. Let's say I want to form this this double bond, and my starting thing is an alcohol. What reaction do I know that can do this? Yes, dehydration. So what's that means going to be on the arrow? Notice now the arrow we're going backwards. Over here we're going forwards. So normally for synthesis, concentrated acid, yeah. So sulfuric acid, H2SO4 / heat. Something like that. You could technically have the OH be on either side. It would give you this answer. But the important thing is you're going to learn this later, but H2SO4, it likes forming internal double bonds. So it won't want to give you a double bond that's like this. It wants to give you a double bond that's how this one's drawn in the middle. There is, however, a reagent, you'll see this in your reaction sheet. There is a reagent that likes giving you terminal double bonds that are at the end. And that one is POCl3, but you'll learn about that one later. Yeah, so H2SO4 will never give you a terminal double bond. It'll make carbocation rearrangements to give you the internal one. Okay, so we learned today, let's implement the last 2 we just learned. Oh, sorry. These ones you might not remember as well because we haven't spent that much time on them. But let's go over them nonetheless. That's not what I wanted to do. All right. So now We have CH2I2 and zinc copper. What do we say that what this does? Try to remember without cheating. Remember? This one gives you, remember, a cyclopropane. And the stereochemistry is preserved. In this case, it doesn't really matter, but looks like that. What about CH2, CH2N2 in heat? What does that one do? So this one, just the same as that one. So that's a nice thing. If you see either of those reagents, you can again categorize these to do the same thing. You use cyclopropane. Same stereochemistry, same everything. Important thing to know, this is called Simmons-Smith. It's like an important reagent. 2 scientists made it. All right, so now, continuing on the subject of cyclopropanes, what does this one make? We just went over this. Give you a hint. It looks like this one that we just drew, except, what's the difference? You know, there's not going to be 3 reagents that give you the same thing. Is it 1 chlorine or 2 chlorines? Yep. This one gives you a dichlorocyclopropane. Looks like that. All right. And then this reaction, I think this is one of the first ones we learned today. What's going to result in this? What's going to be added? Yeah, Br2 and H2O. So naturally, you're going to have a Br being added and an OH being added. Refer to the mechanism in case you forgot how that happens. Remember, you form that bromonium ion, and H2O wants to attack that from that most substituted side. So because it attacks the most substituted side, you get inversion, because it's like a backsided attack. So they're anti. This one's anti, and it's mark, but with H2O. So you get something that looks like this. That's OH on the mark position. OH and Br are anti. That pretty much sums it up. Next one we'll do, we'll leave it as a, let's do one final reaction. Let's learn one final reaction and then we'll end the workshop. The last reaction is a very important one. It's called oxidation of alkenes. So oxidation of alkenes. So this one involves, so the first part, the first one we're going to learn, epoxidation with peroxy acids. So oxidation, epoxidation, peroxy acids, a lot of oxy stuff. So this is a very complicated mechanism, but it's a very important one. So I won't go over the mechanism, but you have an alkene and you have what's called a peroxy acid. So you have, this reacts with C double bond O, some R group, and then peroxy, meaning you have OOH. Notice peroxy, peroxide, CROOR. This is like ROR. This is like peroxide. So it's called peroxy acid. So you have some R group bonded to C double bond O bonded to OOH. And these two, when they react together, they give you something that looks like this. This is called an epoxide. So it's very, very important. So now, the way you'll see this, the most, because again, RC double bond OOH, it's a very generic peroxide, generic peroxy acid. The most famous one that you'll see that will give you an epoxide looks like this. Well, this is the double bond. And again, keep this, you really have to remember this, MCPBA. It's called metachloroperoxybenzoic acid. Metachloroperoxybenzoic acid. So what that looks like, you have a benzene, you have a chlorine coming off in the meta position. You'll learn about that in Orgo 2 if you have to suffer taking Orgo 2. Then you have your C double bond O, OOH. Or sometimes you'll see this written as CO3H. Recognize this. You don't have, like, with this, MCPBA is more than enough. But if she wanted to kind of test you, she could just show you that, oh, sorry, this is a benzene. She could show you this, or she could show you something CO3H. Well, you have to be able to recognize that this is another way to write MCPBA. This is MCPBA, just abbreviation of this thing. This is metachloroperoxybenzoic acid. And this gives you an epoxide where stereochemistry is maintained. So this is called an epoxide, where the O is like, it's kind of like a cyclopropane, but then there's an O instead of a carbon. And stereochemistry is maintained, so you'll have CH3, H, CH3, H. So this is again MCPBA. Okay, so we'll stop there, but the next on this worksheet, we haven't learned enough reactions for me to actually assign a worksheet. So just review the ones we've done so far, and I'll try to see if I can find a worksheet that just has these reactions, like different variations of them. But in general, there's not much else to really practice other than just memorizing whether something is marked, whether it's non-marked, whether it's anti-planar, whether it's syn-planar. Yeah, there isn't much else to this point. Just make sure you can memorize these. Make sure if you saw a double bond with this reagent, you would know what product it gives you. Things like this, and then stuff like this epoxide, carbene, cyclopropane. So yeah, at this point, again, me as like the facilitator, there isn't really much that I'm teaching you. It's just kind of forcing you to stay up to date with the reactions. But as far as memorizing, it's all going to be down. It's going to be up to you to make sure you do that. And that's why with this exam, I'm trying to make sure to kind of force y'all that you're doing it. That's why I think worksheets was a really good idea, just because I can kind of stay on top of where y'all are at, make sure your progress, stuff like that. So I'll make sure this weekend, over the weekend, you get something, hopefully, something assigned that you can do. And yeah, so far the grades I've been getting for the exams have been much better than the first exam, so I'm very happy about that. Hopefully, that means either I'm doing something right or doing something right, a combination of both. But yeah, just hopefully keep up the good work. Again, this exam, it can be hard if you make it hard. That's my logic on it. Obviously, if you don't take these reactions seriously, it's going to be a hard exam. If you stay on top of them, keep practicing, keep up with the workshop, then I don't see why it should be hard. If anything, from what I've seen, some people that really studied these reactions, they find this exam to be easy. So it's up to you whether you want to be one of them or the ones that suffer and procrastinate. So yeah, make flashcards if you want. Again, I gave my rant about flashcards last workshop, but do whatever makes you feel most comfortable. But with that, we'll end for today. Sorry I was late again. Had to go to the fish market. Long story. Fish market is very far. So we'll see you all on Monday. Message me about your exam grades. Hopefully, when you pick them up tomorrow, if you didn't get a chance to pick it up yesterday. And yeah, just keep me posted if you have any questions, comments, feedback, concerns. See y'all.